Thank you, Kano-san and IRC, for this opportunity to be presenting to you today. For those of you who don't know me, my name is Jacques. I'm a Senior Support Engineer at VICON, and it is a great privilege and honor to be sharing with you some of the modeling information that we have available at VICON, as well as give you a practical guide on some modeling options within Nexus. The presentation today will be broken down into 4 sections. The first one will just be modeling introduction. Then the second section, we will be talking about modeling options available within VICON. Thirdly, we will be looking at 2 specific foot models within the Nexus platform. And then finally, we will be looking at the hip and knee models within Nexus. Firstly, a quick introduction. As I said, this presentation will introduce you to different modeling options being used by VICON customers across the world. We will be investigating a few workflows within Nexus, and then I will also introduce you to references. And hopefully by the end of today, you will have a few practical guides on how you can implement what you've seen today in your own modeling and in your own research applications. It's also important to understand what this presentation will not do. I will not be discussing the pros and cons for each model, and we will not suggest or give VICON's recommendation on what model you should be using for your research. In the end of the day, that decision should be up to you of how you design your research and how you apply the model to your research question. So firstly, what is a model? A model is a mathematical relation that allows the foreseeing the behavior of systems that have been modeled given some known inputs and parameters. So we have our model and our output, but what we do need is we need something to put into our model, our biomechanical model, and then we also have some modeling parameters that we need to input. So why do we need a biomechanical model? I love this quote. I think it's a really helpful quote in trying to understand why we need a biomechanical model. And it's from Dr. Scott Delph at Stanford University. He says that a biomechanical model allows us to extract mechanistic insights from messy and heterogeneous movement data and to make predictions in domains where data are unavailable. For example, predicting the response to a future surgery, or possibly even how we can improve athlete performance, prevent injury, and help an athlete return to play. So how do we apply our model to human motion? In the middle of this slide, you can see that we have our model, or a mechanical equivalent to a model. What we do need is we need an input. And what we get from motion capture is we get markers and trajectories, and that can be fed into our model. And secondly, what we do need as well is some inertial parameters. So we have some inertial parameters and marker data, and then from that, the model can give us some joint kinematics or joint kinetics. Now let's look at the modeling options available to VICON customers across the world today. What we do have is we firstly have ProCalc. ProCalc is a VICON provided software for any customer who owns Nexus 2. It's free of charge, there's no extra cost. And at the end of this presentation, I will show you a quick YouTube video on how you can delve deeper into ProCalc modeling. Then we have Python, which is an open source modeling application. We have LabVIEW, we have MATLAB, Motion Monitor, C-Motion. You can integrate with Motec and OpenSim. And then Nexus actually gives you the opportunity to directly integrate through some of these applications like Python and MATLAB using the offline SDK or the VICON Data Stream SDK, which allows you to stream data out of the application and do some real-time modeling. Now, what models do we have available within Nexus? Here's a few models. We have plug-in gate, as I'm sure many of you are aware of. we have CGM2, which is a relatively new model and is beginning to gain more ground within the clinical community. We then have the Oxford Foot Model, we have SCORE and SARA, we have an upper limb model, which was developed by one of our employees, and then we have a whole batch of example models and scripts available on the VICON website. So what are we going to be looking at today? As I mentioned earlier, we're going to start by looking at the foot and the ankle. And by looking at the foot and the ankle, we're going to look at the Oxford Foot Model. So we're going to look at a workflow for the Oxford Foot Model. Then we're going to look at the IOR or Leodini Foot Model. And specifically, we are looking at one that's been implemented by a company called GPEM. Then we will be looking at the knee joint. And there I'm going to show you the workflow for SARA. And then finally, we're going to be looking at the hip joint center. And for that, we're going to look at SCORE. And then right at the end, I'm going to take the information from SCORE and SARA and show you how you can implement this into your own custom model. So firstly, we'll be looking at some foot models available within Nexus. The first one we're going to look at is the Oxford Foot Model. The Oxford Foot Model was originally designed for researchers and clinical gait analysis. And the aim behind it was to assess dynamic motion of the foot. The Oxford Foot Model is a multi-segment, three-dimensional kinematic model, and it was developed by the Nuffield Orthopedic Centre in Oxford in conjunction with Oxford University. VICON introduced this model initially as a bodybuilder script with the help of the Nuffield Orthopedic Centre. Then it was allowed to be implemented into Nexus 1 as a standalone installer, and now we natively install this model within Nexus. The model comes with 3 different marker sets natively within Nexus, and all 3 of these marker sets can be integrated within Plug-in Gait. We have the left foot, the right foot, or the bilateral foot, which will be the Oxford Foot Model. So what I'm going to do now is I'm going to show you how we process the data within Nexus. So here we have Nexus open, and I actually have some data captured already, but this data has not been processed at all. So the first thing we need to do is we need to ensure that we have some reconstructed data. So here we have our reconstructed data, and we reconstruct our data from the 2D camera image by pressing this Reconstruct Pipeline button. And here you can see that we have all our markers available. Then what we have to do is we need to make sure that we have the correct marker set or labeling template attached. What I'm going to do is I'm going to delete this, and then we're going to start from scratch. So we have no marker set available. None of our markers have been labeled. We have on the left-hand side under our Resources and Subjects tab, we have 3 options. We first have a Create Blank Subject, load a labeling skeleton template, and then finally load an existing subject. Now what we want to do is we want to start from scratch, so we need to create a new labeling skeleton. And what we have that gets natively installed with VICON is the left Oxford Foot Model, the Oxford Foot Model AI, and the right Oxford Foot Model. So the marker set that we are using today is the Oxford Foot Model Lower Body AI. When we select that, what we then receive is this pop-up to enter the subject name, and we will just leave this as new subject, or what we could do is just call it subject 1. And then on the left, the subject will appear. Now when I select this subject, I have all my subject measurements that is available with this model. So you can see here that we have all our markers, our subjects, and on the left we have some labels. So the first thing we'll do is we need to enter our marker diameter. Now what we need to do here is we need to know what marker size we are using. Generally, for the Oxford Foot Model, you will either use the 9mm markers or the 14mm markers, depending on whether you're capturing children or adults. And this marker size refers to the markers on the feet. For this specific marker set, we were using 14mm markers. And then we will enter the body mass for the subject. I think he was weighing 78 kilograms, and we need to enter our height. So 1870, and then we'll enter leg length. That was 800. Knee width was 150, and ankle was 120. And then we repeat the same for the right hand side. Anything that is highlighted in pink is a required measurement. So we need to enter that. And this is all needed for the modeling section, not for the labeling section, but only the modeling section. 150 and then 120. Of course, you will need to make sure that you measure these measurements. The chances of someone being perfectly symmetrical is very slim indeed. Then what we need to do is we need to label my subject and make sure that the labeling template gets created. And this, of course, will be assisting with our real-time labeling. So now we have auto-initialize labeling. It's a pipeline, but it's also available at the top as a single button. And what this will do is it'll run, firstly it'll auto-label the subject, then it'll scale the subject, and then finally it'll calibrate the subject for the auto-labeling process. So what we'll do is we'll run the first one. I'm right-clicking and I'm pressing Run Selected Operation. And here we can see that the subject has now been labeled. A quick tip, if you really want to look at the labels, if you hold down Control Spacebar, you can see all the labels for each marker. So this is just a quick method of viewing the labels. So what we'll do is we'll just quickly have a look and make sure everything is labeled correctly, and then go Control Spacebar again to remove that information. Then what we need to do is we need to scale my subject. This scales the template down to the correct size, and then finally we'll calibrate the subject. What the calibration will be doing as well is it'll be removing these yellow markers from the labeling template. So if I expand the template on the left, I can see that none of the yellow markers are available. So now we've done our static calibration, but we haven't run our Oxford Foot model yet. And to do this, we need to select Current Pipeline, Static Oxford Foot Model, and then within that pipeline operation, we have two options. The first one is Process Plug-in Gate. So because what we are doing here is we are using plug-in gate marker set with the Oxford Foot model. So we need to run two models. The first one is running an overall plug-in gate model, and the second one is only running the Oxford Foot model, the lower body section, or the feet. So what we're going to do is we're going to output our joint centers, and my subject was standing with their feet flat. So we'll run this operation, and now we're getting our plug-in gate model outputs. And if I look at the model outputs and the angles, I can see that there's the standard plug-in gate model outputs available for us. The second thing that we want to do is we actually want to run our Oxford Foot model on top of this. And what we get here is, the options we get is the subject's forefoot flat with the floor. Yes, the subject was standing flat. If they are standing in an equinus position, you won't be ticking this box, of course. Is the right foot flat? Yes. Hind foot is flat. Yes. And they are actually traveling in the X direction. So we can see he's facing in X, and X is the red axis. And we select Run. Okay. Now if we expand our model outputs, we can see that we have some model outputs available here. So this is the static process of getting a baseline for our subject. So what we'll be doing is we'll be saving this trial, and then we'll be moving on to our dynamic trial. And I'm going to select trial 2. And here you can see we have 2 force plates, we have all our data, and we have our subject still in here. The first thing we want to do here is we want to run the Reconstruct and Label process. So what this is doing is this is automatically labeling my trial for me. And what I have is I've got the subject that appears. And then if I look in my labeling and edit tab, I can see that we have a few gaps in our data. And this will probably be more than likely due to coverage. So what we need to do is we click on one of the markers. That will automatically jump to where the gap is appearing. So we can see that we are losing this toe marker. We then have 4 options, or 5 options actually, on how we want to fill this gap. This gap is only 1 frame, so we can just use the standard spline fill. And then we select our next gap. And what we want to do here is we have, again, just 1 frame. But you can see that we can't fill using the spline fill. That is simply because there's a second gap that happens right over here. So what I'm going to do is I'm going to use a pattern fill. And if we click Auto, the software will automatically look at the foot and then detect which marker represents the closest placement of the RP5M marker that is missing in the gap here. And you can see here we have our donor marker being highlighted and the marker location of where it's going to be filled in. So we go full here. And then it jumps on to the next one, and we can do the same thing. So now what we have is we've got a completed trial, fully labeled, with no gaps. The next thing we want to do is we want to run the dynamic Oxford foot model. So if I select dynamic Oxford foot model, I can then see that the first process here is combined processing. Now what this will do is this will take all your information and reconstruct and label it again for you. Now because we've actually ran it pressing this reconstruct and label option, I will not be running it again. So we will be unticking this box. However, what we will be doing is we'll be filling some gaps. I mean, we don't have any gaps, so we'll skip this step, and then we will be filtering our data. So what we're doing here is we're filtering our trajectories. Then the next step down is we will be detecting foot strikes based on the force plate. So we can see our subject walking across the plate. We're getting a heel strike and another heel strike and a toe off here. So now what we want to do is we want to take this information and we want to put it across the whole trial. So we will be auto-correlating the events. Then we will be processing the dynamic plug-in gate model, because remember we are using plug-in gate lower body with the Oxford foot model at the same time. So then we want to output, what I'm going to do is I'm going to output the joint centers again, and we run that pipeline. And then finally we will be running the Oxford foot model itself. So here we can see we have our standard plug-in gate output, and when we run the Oxford foot model, we will be getting our Oxford foot model outputs. So there's quite a lot of information in there. And then the final step is we want to export this as a C3D file. Now what we now can do is we can save this trial and open this in our, add this to our quick report, and then we can view it in our quick report. So here we have the tibia angle and the hindfoot angle as well. So we have quite a bit of information here that we can now export to a PDF using quick reports. So this is one model that we have natively within Nexus. But what I want to do next is I want to show to you a different foot model. So let's switch back to our presentation. But before we do the second model, here are some references for the Oxford foot model if you're interested in them. We have the original paper published in 2001. Then we have the paper published in 2005. and then finally the dynamic foot movement in children treated for congenital telepies. So there we have some publications to look into. So now we're going to look at the IOR, or Leodini foot model. The Leodini foot model is also a multi-segment foot model, which was designed for researchers and clinical gait analysis. It was designed by Professor Leodini at the Institute Orthopedica Roselli. The version that we're going to be looking at of this model has been implemented by a company called GPEM, and you can actually download this model from the website, and you will need a license to run it, but you can contact them to find out more about that. And this model was also designed to assess dynamic foot motion. So what we're going to do is, before we switch to the Nexus example, what I want to do is I just want to show you the GPM website. This is a company in Italy. The website is gpm.net, and what they have is they've got different software development options available. And here we have the GPM IOR foot model, and this has been designed to be implemented within Nexus itself. Okay, so next what we'll do is we'll go back to our presentation, and we will be looking at the foot model. So the IOR foot model comes with 7 different marker set options, and it can be integrated into plug-in gait, which is great. You can see there's our list of markers that are available for us. We have the IOR plug-in gait with a sacral marker. We've got both feet. We've got IOR plug-in gait and CAD. We have the left foot. We have the left foot plug-in gait and CAD. We have the right foot, and then we have the right foot plug-in gait and CAD available. So now what I'm going to do is I'm going to switch over to Nexus to look at the workflow for the IOR model. Okay, so let's close this trial from earlier. And we'll go up to our database. Here we have our IOR foot. And I'm just going to select a static trial. Okay. So we can see we have a trial open, but we have no data available. Now, first thing we need to do is when you use the IOR model, you will need a license to run it, as mentioned earlier. And to do this, you need to run this little Python shell. So you run this, you will then get this little pop-up, and this will explain to you how to request a license and also how to activate a license. So you can see here, I currently have a license that is expiring next year. So we will just be moving on, and I'll show you how to run the model. As I mentioned, we already have the trial open. So we will be reconstructing our data. And here you can see we have all the markers. You can see there's quite a few markers. Well, quite a lot more markers than the Ocst foot model. And what we have is we only have the feet. We only have the left and the right foot. So what we'll do is we're going to do both sides IOR foot and subject 1. And here we have our little VST that's loaded in. I'll mark the diameter, and then we have an offset subtraction that you can run as well. So now we're going to run the IOR static. So when we get here, you can see that our model is not labeled yet, but we need to have it labeled. So what I'm going to do is I'm going to switch to the auto-initialize pipeline, which is a default option that's available within VICON. And it's the same one which we actually used for the Ocst foot model. And I'm just going to run this. So you can see here we have our calibrated process. Then we're going to go to the IOR foot. And the first thing we can do is run the calibration. Then we're going to run the Python script to initialize the model. Okay, so now we have created some modeled markers. Then we're going to run the actual IOR model, which is a body language model that's been implemented in the pipeline. And we'll be running this. And here we have our outputs for the IOR foot. And then finally, we will be saving this pipeline. So this is just a pretty simple process. You can see that it's the same as running it within the Oxford foot model. The static process is exactly the same. So what we're going to do now is we're going to save this trial. Actually, we've already saved it. So we then open our dynamic trial. And then we're going to switch to the IOR dynamic. So the first thing we need to do is we need to reconstruct and label our data. So you can see we have no information, but you can see when the subject is walking across the plate. So we're going to do reconstruct and label. Okay, so here we have our subject. Then one thing we haven't done with this pipeline yet is we haven't filtered our trajectories, which will be a good thing to do. And if we go to filter trajectories, we'll just do a watering filter, and we'll move this up to the top of our pipeline. Then we will be detecting our force plate events based on the heel strike. So we can actually see we have a double strike here, a double toe off. So what we'll do is to correct that, we will just jump to the next one where it thinks we have a toe off, and I'll delete that. Then we will take this event information that we already have here, and we will autocorrelate that to get it across the whole trial. So here we can see our force plate activity, and then we're going to run the dynamic model to initialize the Ior model, so you get our reference point there. And then we'll do the same for these two trials. So here we have our Oxford foot model, the IOR foot model processed. So you can see a really simple process, pretty much the same as the Oxford foot model, but it'll give you a slightly different information out. So I think it's a great way, especially if you only want to look at the feet and you're not interested in the pelvis, this is a great model to be using. And the same way we can add this to our quick report, and we actually still have our plugin, our Oxford foot model available. So if we just look at the information from this trial, we can see here's some information available there. So apologies, not that one. There we go. So this will be our angle. And that is the IOR model. So if we switch back to our presentation, here we have a few publications based on the model. As mentioned, it is the Leodini, also known as the Leodini model. Please, I would encourage you to have a look at this model if you are interested in doing research in the feet. It is really a great model to be using. Next, what we're going to be looking at is the hip and knee models within Nexus. Now, a few of you will already be aware of this model as it came out with the original launch of Nexus 2 in 2015. However, we thought it would be a good idea to give you a little refresher of this model and how you can implement it within your process. So what we have the score and SARA method. It was originally designed for researchers and clinical gait analysis, and I'm actually aware of a few researchers who are actually using this in sports, especially the SCORE method to look at the shoulder joint center and even the elbow angle of, axis of rotation. So this is an optimized algorithm to estimate the center of rotation and the axis of rotation. It was originally implemented by the University of Berlin and the Julius Wolff Institute for Biomechanics. And it uses a range of motion to calculate around the joint to implement the joint center and the center of axis. So here we have a quick little video showcasing you what is needed. The first thing that we'll need is it's a star arc movement. So I'm going to be running through that process with you in Nexus, and you can see the movement that the subject is making. And this will be a real-time output that you get as well. Then we have the scroll method. That's the second method that we'll be looking at. So we can see the joint centers being calculated here. So there we have our hip joint centers. And then the second method we're looking at is the Ior method, which calculates the knee axis of rotation. So what we're going to do now is I'm going to switch to Nexus so that we can look at the workflow. The beauty of using the score and Ior method is that this method can be implemented within plug-in gate, but not only plug-in gate, you can actually implement it into your own model. And you do not have to use the standard plug-in gate marker set. Now, the marker set that we're going to be using today is the plug-in gate marker set. Let me just delete this subject quickly. Okay. So what we have is we are using plug-in gate lower body. Let's just double check. Apologies, we're using a full body. What we're doing is we'll be doing plug-in gate full body AI functional. So this is a functional VST that we're entering in. And exactly the same method as we've done with the previous two models we looked at is we first need to do some labeling. Now, what we have is we have the advanced gate workflow static. Now, because we have already processed it, what the model will be doing is during the static process, it'll be calibrating our clusters that we have. So if I run the first step, apologies, there we go. So if I run the first step and we label our trial, what we get is we get these three markers on the thigh that creates a cluster. And within our pipeline, what we need to do is we need to assign these three markers as a shape, as a common shape. So the method we do that through is the OCST method. So it's a optimized common shape technique. So we've done our calibration. So we can untick these first few. So now what we want to do is we have our pelvis. So what the system will be doing is it'll say the pelvis forms a segment, a cluster. So we'll be running the first one. And what you can see here is we get this bone that gets created. And if we look at our subject, we can see that we now have an OCST bone called pelvis. So what we'll do is we'll do the same for the femur, for the right side, and that is using these three markers. So it's using these three markers, the thigh A, and the knee marker as my cluster. And we'll be repeating that for the left femur, the tibia, left and right. So now we have our calibrated subject. Now what we have to do is we save this trial and we go to our left hip. So what I'm going to do is I'm going to run it just on the left hand side because I want to show you how we can implement it into our model. So the first thing we do is we do Reconstruct and Label. And when I play through the trial, you can see that the subject is doing a star arc method. So we're going to do we're not going to do the combined processing because we already have it labeled. But now what we do is we process the OCST. Remember, on the first step, we calibrated the OCST. Then we're going to process the femur. And now what I'm going to do is I'm going to calibrate SCORE and SARA. That means I'm going to calculate my hip joint center. There we go. So there we have our left hip. So this will be our hip joint center. Now what we'll do is we'll repeat the process for the right hand, for the knee. And we'll do Reconstruct and Label. And what we get here is we can see that the subject is flexing and extending the knee. And then at the end, they do a squat and then go back to normal. And to run this on the knee, we need to change our pipeline again. So we change from Advanced Gait Workflow Left Hip to Advanced Gait Workflow Left Knee. And we won't need to run the combined process, but the steps would be the same. We process our OCST, and then we calibrate the SCORE and SARA. So we run pipeline from selected operation. And what we now get is we get this knee axis of rotation. So this doesn't calculate the angle. It simply gives us an axis that we can then use within our model. So we'll save this trial. And we'll move on to the walking trial. Let's use this trial here. So what we've done is we've only done the left-hand side, but you can run the same process on the right-hand side. So what we're going to do is we're going to reconstruct and label the trial. Okay, and what we'll do is we'll just make sure that we can fill the gaps. Quick way to fill your gaps would be to run the auto gap fill pipeline. Okay, so here we have the data processed and all our gaps are filled. So this pipeline operation here runs via this pipeline here. And this goes through all the markers that we had here in a step-by-step process. So this is the final output that we get. So we still have one gap, and it's right at the end of our trial. So we're not too interested in that. What we're mainly interested in is this section over the force plate here. So the next step, what we need to do is we need to process our dynamic trial based on the information that we have for our static. So we go Advanced Gait Workflow Process. Okay, we don't want to reconstruct our data again, but what we do want to do is we want to process the pelvis. We want to process the left femur. Remember, we only did the star arc for the left-hand side. And then we'll do the same for the tibia and the left hip and the left knee. So here we go. What does this give us? This gives us the knee axis of rotation, and it also gives us the knee joint center. Not the knee, the hip joint center. So let me just save this trial and we'll reopen it so that we can see a little bit clearer. Here we go. So here we have our hip. And now what we need to do is, how do we implement this into our model? I think that's the next big question, correct? So what we're going to do is we're going to open up MATLAB. And what we have here is, you can see, I've got a little script that imports the VICON offline data stream SDK. So I import that, I create my subject, I then read some marker names from my trial. So I'm reading the left-hand side, and then I define a segment. So I'll go into this in a short while. The first thing I want to do is I just want to run this as a pipeline to show you what we get. Okay, so the pipeline is complete, but now if I go back to Nexus, we get this left knee angles. So let's see what that looks like. Here we have our left knee angle, which is great, right? The problem that we have with this specific one is that it's not actually using the hip joint center that we calculated or the knee axis of rotation. What it is using just the marker positions themselves. So we're not using any of our calculated information. So the first thing we need to do is we need to make sure that we can read some of the new data that we've created. So we're going to create firstly the pelvis, and that'll be pelvis left femur underscore score. And this name that I'm reading here is actually this marker here. So you can see it matches up this name with this name here. Then what we'll do is we'll go equals Nexus trajectory. So that is telling MATLAB, go and look at the Nexus .m files. Here's one called Nexus trajectory, and use that information to extract the marker. Trajectory. And then we need to give it enter our subject name. Now here we have sub J11, but our subject is actually called subject 1. By writing sub J11, I'm actually using this information here, where I've already went and grabbed the subject name. So I'm just using this command here and putting it in there. Sub J, curly bracket, 1, 1. And then we'll do a round bracket. So what we'll then do is we'll repeat the process for the femur and the tibia, because we want to calculate the, not the femur and the tibia, I mean the two markers that we have here. The two markers we calculated from the SARA calculation. So this first one and the second one. Okay. So we have left tibia score. So L femur underscore L tibia. So that's the one. And then we'll do the same for the SARA section. So I'll just copy that. And we'll do the same for SARA. What you then can do is you can read, well, we need to read the information that we've just created. So we'll just copy that across and put that on there. And that'll read the information. Now what we need to do is we need to define a segment. So here we have a segment that's been defined as left thigh. Now what I want to do is I want to define a segment called left thigh SC. So what we'll do is well, the reason why we'll call it alpha SC because that'll stand for score in SARA. You can name it any name you want. It's just for me slightly easier to understand what I'm looking at here. So we'll do SC. So that'll be a thigh that I'm creating. And then I want to populate that. I want to actually do the calculation. Now, for those of you who've been using Bodybuilder, you might recognize this, because what we have is we have our origin. So, and I'm going to make the origin the pelvis marker. So this marker that we have here, this will become my origin for my thigh. Instead of having my origin at the knee, ideally you want it at the knee, but for now I'm going to put it at the thigh. So that'll be our origin. Then we will be starting at the SARA marker. Actually, we want to end up at the SARA marker, apologies. And we'll put that in there. And then we'll do the same for the score. And then we need to do our access order. So our first axis was actually X, because that refers to this axis here, and that is our X axis. So what we have is we have X, Y, and Z, and then what we want to do is we want to calculate the angle between them. Okay, so now I've created a segment, and then what we need to do is we need to calculate an angle. So we're just going to copy that information that we have down at the bottom here, and we're just going to replace the ML with SC for score and SARA. And then instead of using the left thigh, I'm going to use the left thigh score and SARA to do the calculation for me. And then the access order that we're going to use is X, Y, Z. So we're using a slightly different access order. So now what we can do is, if we go back to our model and we delete the information that we've created, so we've got no angle output anymore, and we run this, and then go back to Nexus, we have our two angles. So you can see that if we just look at the X angle, that there's a slight difference between the two processes, and that is because we're using a different axis of rotation as well as a different origin. And then you can go one step further if you really want to, and you can, instead of writing the information back into Nexus, you can run the information and you can get your output within MATLAB itself. So here we have our x-axis, y, and z based on score and SARA method that we used. So that is the score and SARA method that we've been looking at. Here we have a publication of the first one. It is the OCST method. Then we have the publications for score and SARA themselves. Just a brief recap. We've looked at the Oxford foot model, the IOR foot model, and then the SARA method, the score method, and the OCST method. All these methods are compatible with Nexus. They all can be used with MATLAB by reading the outputs that Nexus gives you through the Nexus offline data stream. They're also compatible with Python in the same method as with MATLAB. And then some other resources, they can all be integrated with plugin gate. And then score and SARA and OCST, you can also apply that information to your own model, whether it is a sporting activity or clinical work within a hospital. You can still use the score and SARA method in that. Then finally, I would like to point you to the following 4 resources. Over the summer, we were part of a presentation for the International Society of Biomechanics, and we presented some presentations on motion capture hardware, software, and modeling, as well as a workflow on how to do motion capture entitled Let's Do Some Motion Capture. And then something that's really would be of real benefit for you all is this final presentation here at the bottom, which is a presentation which was done a few weeks ago by my colleague in America. and they talked about VICON Pro-Calc and unlocking the full power of Nexus by integrating Pro-Calc modeling into your daily biomechanical research. And then finally, we have the VICON Life Science YouTube channel. Please do subscribe. We will be adding more information over the next few months. And if you do have any suggestions or questions, please do feel free to contact me. That brings me to the end of my presentation. I know that Dr. Kim Duffy, our product manager, will be available to answer some questions for you. Once again, it's been an honor and a privilege to be presenting to you today. Thank you.